Before we can study digital communications, we have to have a firm basis in our understanding of linear systems, because this is some of the fundamental assumptions in the analysis we'll be doing in the digital communications class. For this reason, I take a little time to go over linear time invariant systems, LTIS, sometimes they're known as a review before we dive into our digital communications. So this information is covered in the Scholar textbook in section 1.6. So we start by what is linearity. So a linear system is a system where a linear combination of inputs generates the exact same linear combination of outputs. That is, if I start with an input of x1, I put it into my system and it gives me y1. Now I start with a different input, x2, and I put it through my system and I get y2. That means if I take any linear combination of x1 and x2, so I have ax1 plus bx2, if I take that sum of signals and put it through the exact same system, I will get the same linear combination of outputs, ay1 plus ay2. Linearity. An example would be an ideal amplifier. An ideal amplifier would take the input signal and simply multiply by the gain R. So in this case, clearly it's linear. A counterexample would be a square law detector, for instance, a photodetector. In this case, the output of the system is equal to the input squared, so clearly not linear. Time invariance is the other part of the LTIS, and the idea of time invariance is that an input lag causes the same lag at the output. So again, if I put in x1 of t, and at the output I get y1 of t, then if at the input I send the exact same signal but with a lag of tau, at the output I'll get the exact same output, but this time with the same lag. Again, a good example would be an ideal amplifier. So it's just multiplied by the gains, so if there's a lag, clearly it's also there. This counterexample is a little touchy, but the idea is here the phase of the sinusoid that I'm multiplying by. For instance, here, sinus at sine t, the sinus is at t equals 0 is 0. So if I introduce a lag at the input, if it's not exactly 2 pi off from the t value, then I'm going to get something that's not invariant with it, so that I will be multiplying by a sine function, but this time a sine function with a different phase. So this would be not a time invariant system. So a linear time invariant system we also call a filter. So filtering, by definition, is the same as passing our signal through a linear time invariant system. So here we can represent our system as a black box. And this black box is completely described by a mathematical expression. So for instance, if we look in the time domain, we have a time varying signal, the input to our system. At the output, we have another time varying signal. And we represent this system by a function that varies in time, which we call the impulse response. So I really don't care what's inside of this black box, which is my system. If it's a circuit, for example, there are different kinds of components that perhaps will give the same impulse response. And I don't care which components are actually used, because I can describe that entire system by this mathematical expression, the impulse response. Now, when we're doing analysis of linear systems, we often like to use the Fourier transform. So for instance, if I take the input signal, I can take this time varying signal and look for the Fourier transform, which gives me the frequency domain properties of this signal. So I can represent it in the time domain, or I can represent it in the frequency domain. The same thing with the output signal. This time varying signal I can represent by its Fourier transform. So the system itself, I do the same thing. I take the impulse response in the time domain, and I calculate what is the Fourier transform. And in fact, I have a name for this. I call this the frequency response of the system. So in this representation of a linear time invariant system, I can do the entire representation in the time domain, or I can do it entirely in the frequency domain. Of course, we know that there's this one-to-one property for the time domain and frequency domain. So if I specify the impulse response, there is exactly one frequency response associated with this. So that each one is unique. This pair is the Fourier transform pair. So there is an input-output relationship that I can very simply write in the frequency domain. Very simple representation, and therefore this is perhaps sometimes the first time we see what is the definition of a filter. A filter is such that the ratio of the output Fourier transform divided by the input Fourier transform gives the frequency response of the system. So whatever input I use, I can change the input of my system, but the ratio of the output to the input is always going to give me this frequency response. So this is because it's a linear time invariant system, so all of this is tied together. But this is the definition of a frequency response. It's the ratio of the output divided by the input in the frequency domain. And of course, I said that the impulse response we could find by the inverse Fourier transform because it's a unique pair, the Fourier transform pair. I could start from h of t, calculate the Fourier transform, and get h of w. Or I could take h of omega in the frequency domain and take the inverse Fourier transform. Here's the integral that gives the inverse Fourier transform, and that will give me the impulse response. So if I wanted to look then in the time domain, what is the relationship input and output? Well, it looks a little more complicated because it's the convolution, which is of course an integral. So it's here it's just a division, very simple division, which is why we like to do our analysis in the frequency domain. But in the time domain, of course, there is another way of doing the analysis, and that's with the convolution integral. So perhaps the convolution isn't too fresh in your mind, so let me remind you about the convolution operation. The convolution operation is on two time domain signals. So we take f of t, g of t, and we define the convolution of these two, which will be, again, a function of time. And it's defined by the convolution integral. The convolution integral, it's a definite integral from minus infinity to infinity. And we introduce the dummy variable of integration u. So we take the first function, f of u, and the second function we flip. We flip it by putting a minus sign in front of the variable of integration u, and then we slide it by introducing a displacement t. So this product of the first function and the second function, we integrate. And of course, it's a definite integral, so after the integration, u will have disappeared. However, t will remain, and that's why it remains a function of t. If we think about the graphical interpretation of the convolution integral, the idea is you have f, and then you take the function g and you flip it, and then you slide it along the other function, integrating so that at different points of sliding you get different values of function of t. So that's the definition of the convolution integral. Now let's look at one property of the convolution integral, and that is that it has an identity operator. And the identity operator in this case is the Dirac delta function. So what is an identity operator? That means if I take the delta function, convolution any function, I get the same function back. So let's see why that's the case. So the Dirac delta function, let me make this maybe a function of z. The Dirac delta, we call it. What is the definition of a Dirac delta function? Well, a Dirac delta function is equal to 0 whenever z is not equal to 0. Okay, that's one part. I don't say what it is, it's equal 0, but I'll tell you what I do say is that if I take the integral of this delta function, I will get 1. So I know that the area under the curve is 1, but I really don't know, it's not really defined at the origin. Okay, so that's the definition. And this definition gives what we call the sampling property. Let's think about what does this sampling property mean. Suppose that I have g of z times delta of z. Well, what does that equal? Well, I could say this is equal to, excuse me, g of 0 times delta of z. Why can I say that? Why are these two things still equal? It's because every time z is not 0, this delta function is going to be 0. So it really doesn't matter what g is because it's going to be multiplied by 0. Now, I don't know what delta function is at z equals 0, but whatever it is, it's going to multiply by g of 0. So that's the sampling property. So now I can show you why the delta function is the identity element for the convolution. So let's just put f equal to the delta function in this definition of a convolution integral. So I replace f by delta. Now I have the product of these two functions, and I'm going to use this sampling property. So I know that I'm multiplying this delta of u by g of t minus u, and so the only value of g that matters is when u is equal to t, because then the argument of g will be 0. So at t, u equal to t, that's the only value that counts. So I can put in here g of t, so I could have written this as delta of u times g of t, because that's the value when u equals 0. So this g of t is no longer a function of u, so it doesn't have to stay inside the integral. So I can remove it from the integral. I put the g of t on the outside of the integral. And now what do I have left? I have this expression. So this integral is just 1, so the output is g of t. So we've seen that the delta function is the identity element for convolution. And that really is the origin of the expression, the impulse response. I said we had to give a name to this time domain representation of our black box system. So if I take an input, so that the input to my system is a delta function, I put in an impulse. A delta function, it's an impulse. So I put in an impulse. What do I get out at the output? Well, I just get this function h of t. So in the laboratory, for instance, that would be a way of characterizing my system experimentally. I could input an impulse response, very, very short pulse, and measure at the output what is the time domain response. So the output, when the entry is a direct delta function, is by definition the impulse response of the system. And here's a little block diagram that gives the idea of that. Impulse response in, a filter which we can represent in the frequency domain, or of course in the output we would observe the time domain impulse response. So let me go back to Fourier theory again, because there's an interesting result there that we must use in order to really understand what's going on with our time domain signals, to really interpret them well. So let's start with Parseval's theorem, which starts with a function of time, which is an square integrable function. So here the notation is we say it's in L2. The 2 means the square of the integral, and across the whole real line. And we give a name to these kinds of functions, this collection of functions, and that's saying it's an energy function. Energy function means that the function f of t is in L2. Because we have this interpretation, because we think of f of t as a voltage going through a unit resistance, and so when I take the square version of this function, it's like, and I take the integral, it's like measuring the energy of that signal. You'll notice I use the modulus because I allow for the function of time to be a complex signal. And that's convenient in my analysis and communication. So we always try and keep that possibility open as a way of representing signals in the future. So f of t, here we're taking, we allow it to be complex. We say it's square integrable. By definition, that means that this total energy is finite. That's the idea of saying it's an L2. And if it's finite energy, we call that an energy signal. Now, what does Parseval's theorem tell us? Parseval's theorem tells us if we take this integral in the time domain, that it will give us the exact same result as if I had done the calculation in the frequency domain. So I have a function f of t, it's in L2, which certainly means that the Fourier transform exists. So if I find the Fourier transform, f of omega, and I take f of omega, I take its modulus squared, take the integral, there's a little normalization factor of 1 over 2 pi, it will give me the same result. Okay, so that's kind of cool. I can calculate it in the time domain, I can calculate it in the frequency domain. But that's not what's really cool about Parseval's theorem. What's really cool is that I look in the frequency domain, and in the frequency domain I interpret this as a way of looking at how the energy is distributed among different frequencies. Very, very important concept. So I take this thing that's under this integral, so this f of omega, the modulus squared divided by 2 pi, and I call that the energy density. It's how the energy is distributed across the frequency domain. So the spectrum is a term we give for the distribution across frequencies. We call that the spectrum. So the energy spectrum is by definition 1 over 2 pi times the modulus squared of the Fourier transform of the function. So this expression. And this is so cool because that means that I can now talk about how much energy is isolated in a specific band of frequencies. So not just at a particular frequency, not just a precise value of f omega. What's interesting is I can say how much energy is there between 100 and 200 megahertz, because maybe that's the band that I'm going to allow a signal to occupy, and I'm not going to allow it to occupy any other part. For instance, this is a concept that's very important for digital communications. So Parseval's theorem allows us to define a spectrum, and from the spectrum we can have this concept of how much energy is in a band. And the way we find it is, of course, to take the integral of the energy spectrum across the band of interest. So let's start looking at what happens if I take a signal and put it through a linear system. What happens to its spectrum? So I've talked about the spectrum at of a signal. So I can think of x as, for instance, the input of the signal. So I take an input, x of t, for instance here, and I find for x of t what the energy spectrum is, and I'm going to give that a name, and I call it g of x of f. Okay, so this is the spectral density, the spectrum at the input. I know that my linear invariant system has this frequency response, which I call h of f, and what's really cool is that for a linear time invariant system, I can easily find what is the spectrum, the spectral density at the output of my system, and it's given by this simple relationship. So I take the input spectrum and I multiply by the modulus squared of the frequency response of my system, and that tells me exactly what the spectrum is at the output. So we can see why Fourier analysis is like really important in digital communications. So let's take a specific example. Let's look at the response when the input is a very special signal. It's just a cosine. It's a tone, a single frequency. So I take a signal at the input which has f0 as the only frequency content. The only frequency content I put into this system is f of 0. So this system, what happens when I put it through, this cosine, put that through this system? Well, what happens if we do the math is that I get another cosine out. The cosine can be changed, but the only way it can be changed is its amplitude could be changed, and the amount that the amplitude will be changed is by the frequency response at that one frequency. So if I look at the system described by this impulse response and the corresponding frequency response, I take the frequency response at one frequency, that amplitude is going to multiply that cosine at the output. And also if I take the argument, because this frequency response can be complex, if I take the argument of that, it's going to change the phase. So what am I saying here? Cosine in implies cosine out. That's what this is saying. But things can change as the amplitude can change and the phase can change. These are altered. And how are they altered? Well, how they are altered completely determined by h of f. So I only need to know h of f, and now I'll know how that cosine is altered. So put in a cosine, get out a cosine. Amplitude changed by the amplitude of the frequency response, phase changed by the phase of the frequency response. So one frequency in, one frequency out. So now let's think about this, one frequency in, one frequency out, And this property actually has a profound implication. And the implication is what we call bandwidth conservation. That the bandwidth of a signal at the input limits the bandwidth at the output also. So in other words, no new frequencies can be created. And we can see this right away from this simple representation. So before I said that h of f was the ratio of output to input. Another way to put it is that the output is the product of the frequency response times the input signal spectrum, Fourier transform. So in this case, that means if x of f is 0 for a certain frequency, x of f has no content at a certain frequency. So if that is 0, then it doesn't really matter what my system does. It's going to be multiplied by 0, so the output's going to be 0. So that means that no new frequencies can be created. The only frequencies I can have at the output were frequencies which were already present at the input. That means if I have a band-limited input, I have an input which is limited to certain frequencies and 0 for other frequencies, that the output will also be band-limited.